Today's lesson is Dynamics Lesson 5. We're going to talk about friction and frictional forces. So there's two types of friction that we're going to talk about. Remember, friction occurs due to contact between two surfaces, and it always goes against the motion. So static friction is the first kind of friction we'll look at. Static friction is a force that opposes the start of motion. So the word static means at rest, basically. So if you're an athlete and you're doing static stretches, that means you're just standing in one place while you're stretching, whereas dynamic stretches means you're moving around. So static means that you're at rest. So static friction is the force that opposes the start of motion. Okay, so it opposes the start of motion. Frictional force is equal in magnitude to the applied force and opposite in direction. Okay, if the applied force increases a little bit, so if you have a block that you are trying to push, so I'm going to apply a force to this block, okay? So if I just rest my hand a little bit, it's not going to move, but I'm going to increase pressure, increase force, until I get that object to move. So as the object is at rest, your applied force is going to go up a little bit, up a little bit, up a little bit. The object is not going to move until we get to a certain amount of force where the object will move. Okay? So if the applied force increases by a little bit and the block doesn't move, that means both the applied force and the static friction force are going up, until you get to a point where the block finally breaks away. Okay, and we call that the maximum static frictional force. Okay, it doesn't matter how much of the objects are in contact with each other. It's not like there's more or less friction if you have more surface area touching versus not much surface area touching. But the maximum force, the maximum static force, is proportional to the normal force. Normal force depends on the mass of an object, okay? Remember, normal force for an object that is just at rest is equal to gravity. Gravity force is equal to mass times your gravitational constant. Okay, so basically the heavier an object is, the more friction. So the heavier the object is, the more static friction. Okay, so the force of static friction is found by multiplying the coefficient of friction between the two surfaces by the normal force. This coefficient is relevant when the object is at rest. Okay, so force of friction is equal to the coefficient of static friction times the normal force. Okay, so the force of static friction is equal to the coefficient of friction multiplied by normal force. This little symbol here is mu, and it represents the coefficient of friction. Okay, we can rearrange this for mu by itself. So if we want to get mu all by itself, we're going to have to divide both sides by the normal force. So the coefficient of friction is a ratio between the force of static friction and the normal force. Okay, so mu is the coefficient of, static friction. Okay, and it has no units. Okay, the reason there's no units is because force is newtons and force is newtons, so your units would actually cancel each other out and you'd be left with no units overall. Okay, we also need to keep in mind Fn is often equal to gravity. So as long as you know how heavy the object is, you can figure out the coefficient of friction, or you could figure out friction. Okay, so this equation, we'll look at how we use it in example problems on the next page. Okay, so static friction, main takeaway is that it's for objects that are at rest. They're not moving, they are sitting in one spot. Okay, now once the object is in motion, so let's say you pushed with enough force to overcome the maximum static frictional force, once the object is in motion, we call it kinetic friction. So kinetic friction is defined as a force that opposes the motion between two surfaces that are moving. Okay, so once you're in motion, we forget about static force and we talk about kinetic force. So again, doesn't matter how much contact the area, like how much contact area is between the two surfaces, that doesn't really affect friction. It also isn't really affected by speed as long as the speed is slow. Okay, and then the magnitude, or the amount of the kinetic force of friction, also is proportional to the normal force. So as one of them goes up, the other one goes up too. So we're going to use the exact same equation down here that we just made, except instead of static friction, we're talking about kinetic friction. Okay, so kinetic friction is equal to the coefficient of friction multiplied by normal force. Now the cool thing is coefficient of friction depends on the surface. So a lower coefficient of friction means that there is less friction, whereas when you have a higher coefficient of friction, you have more friction. So this number is usually a decimal number. It's usually like 0. whatever. But yeah, so we rearrange this and we get the coefficient of kinetic friction is equal to kinetic friction divided by normal force, okay? Where this time mu k is the coefficient of kinetic friction. Okay? And again, no units. It's just a ratio. Okay, let's look at a couple of examples. We have a skier that's being pulled along a surface at a constant speed with a force of 50. What is the mass and the weight of the skier? Note the coefficient of kinetic friction of skis on snow is 0.050. All right, well, let's write down what we know. We know that we're looking for mass, we're looking for weight. So we're looking for M and we're looking for Fg. They're being pulled at a constant force of 50, so that's going to be our applied force. Now, constant speed means there is no acceleration, which means there's no net force. So if there's no net force, that means our forces have to be equal that are acting on the object. So here's our skier. There's going to be an applied force. Okay, but because there is no acceleration, because the skier is moving at a constant speed, that means that the force pulling the object along has to be equal to the force that's going against it. So what that means is our friction is going to be equal, but in the opposite direction, okay? So the applied force is equal to friction because there's a constant speed, or no net force, okay? So really what that means is we know that friction is also 50 newtons, okay? Applied is to the right, friction is to the left. That's the only difference, okay? So if we're looking to find Fg and we're looking to find m, let's remember that weight or force of gravity is equal to the mass times the gravity. Okay, well, we actually don't have mass, so we can't quite do this yet. But to find mass, maybe we need Fg first. So let's see if there's another way we can find force of gravity. So because this is at rest on a nice flat surface, we know that Fg will be equal to the normal force, right? Normal force goes up, and we've got gravity going down. And they're equal, but they're in opposite directions, okay? So knowing that, maybe we can find normal force. Let's see if there's a way we can find normal force. Well, we just learned a formula where friction equals the coefficient of friction times normal force. Okay, we're not going to use. We could put in our quote. We could put in the subscript. We could say because it's in motion, that would be kinetic friction. So we could really write it as FFK equals mu k times normal force. Okay, we know friction. We know the coefficient of friction that I didn't add to our list. So we can actually solve for normal force. So 50 newtons is equal to 0.050 times the normal force. Now to get normal force by itself, we're going to have to divide both sides by 0.050. Okay? 50 divided by 0.05 is 1,000. So normal force equals 1,000 newtons. Okay? Now we still have to go back. So I'll call this was step 1. Step 2 is we're going to have to go back and use this equation. Okay? So now that we know normal force is really equal to gravity. So once we know Fg, we can go back and solve for m. Okay? So 1,000 newtons equals mass times 9.81 newtons per kilogram. We are going to divide both sides by 9.81. Divide by 9.81. So 1,000 divided by 9.81 gives us 101.9 or 102. Kilograms. Okay, so let's kind of go back and write out what we just found. So the weight of the skier, weight is Fg, which, well, we know normal force is 1,000, and we know that normal force and gravity are equal to each other. So that means that the weight is 1,000 newtons, okay? The mass is going to be what we found using this, right? Fg equals m times g. G on Earth, always 9.81. We found force of gravity to be 1,000. We solved for m, and we got 102 kilograms. Okay? And the reason we were able to do that is because we have the coefficient of friction, so we were able to solve for normal force. And then using our assumptions that normal force is equal to gravity, we were able to go back and find mass. Okay? All right, a 53 kilogram box is slowed by friction. If the force of friction on the box is 5.3 newtons, what is the acceleration? Okay, we have a mass, 53 kilograms. We have FF, so we have friction we are looking for acceleration. So if we want to find acceleration, we need to know what our F net is. Well, the only force it tells us about is friction. Okay, so if we had our box, force of gravity is going to go down, normal force is going to be up, and they're going to be the same. Okay, the only force acting on this object is friction. Right? These two are equal and opposite, so they're going to cancel each other out. So really, our friction is the net force because it's the only force that is unbalanced. Right? Fn and Fg are equal, so they cancel out. All we're left with is the friction as our net force. So maybe somebody pushed this box and then they stopped pushing, so it's sliding to a stop, or it's coming to rest due to friction between it and the floor. So if we're looking for acceleration, we can use F net is equal to mass times acceleration. So F net is our friction, which is 5.3. Mass is 53 kilograms. And acceleration is A. We divide both sides by 53 kilograms. 5.3 divided by 53 gives us 0.1. 0.10 meters per second squared. Or, because it's slowing down, it's back, right? The object is slowing down. So if its motion is in that direction, friction acts against it. So if our motion is to the right, friction is to the left. And so really, because we're decelerating, it's a negative acceleration. Okay? What we could have also done is said that friction was a minus because it's to the left. So we could have said that this is a minus 5.3 newtons, okay? And that would have given us a negative answer. So you just have to remember words like slowed. That means it's decelerating. Okay, so it has to either be negative or you have to say back or left. Okay, this next example is a good one. You wouldn't necessarily need to be able to replicate this on an assignment. It's just kind of an FYI. So I used to drive a 2007 Honda Civic, loved it, manual transmission. Made me feel cool when I was driving around, so sometimes I'd like rev my engine and aggressively drive at a red light. But most of the time I was just out for a leisurely drive. So we're going to find the acceleration of my car during burnout versus when I don't burn out and I just accelerate like normal. We have a coefficient of static friction, and we have the coefficient of kinetic friction. And we have a note that when you're burning out, the tires are spinning. So we're going to use kinetic friction. But when starting normally, the tires are pushing against the ground, and we're going to use the coefficient of static friction. So let's write our information. The coefficient of static friction is 0.75. The coefficient of kinetic friction is 0.67. We're looking for acceleration. Okay. Well, if we wanted to find acceleration, we could use F net equals mass times acceleration, but we don't have mass. And without mass, it's going to be really hard for us to use the formula. And we don't really have a way to use mass. We don't know how heavy the car is. We don't know the weight of the car. Well, let's think about it like this. So the net force that's going to be acting when I'm at rest and trying to drive is going to be friction. So when I'm trying to get in motion, I have to overcome the friction. So really, in this situation, the net force is going to be friction, okay? So therefore, we can rearrange this formula so that friction equals mass times acceleration, okay? Now we know that friction is really equal to the coefficient of friction times the normal force, okay? Normal force is really equal to Fg, which is really equal to mg. So stick with me, we're going to rearrange this equation just a little bit. So really, friction is mu times m times g, okay? So this whole thing here really turns into mu times m times g. Okay, we're going to go back here. Force of friction is equal to mass times acceleration. We're going to replace Ff with mu times m times g. Mu times m times g is equal to mass times acceleration. Okay? Now notice we have mass on both sides of the equation. So they cancel out, right? We divide by m on both sides and our m's go away. So we're left with mu times g equals our acceleration. So let's look at the two different scenarios. Let's look at burnout. So at burnout, acceleration equals mu. Now burning out is kinetic. So mu k times g, which is going to be 0.67 times 9.81 newtons per kilogram, or let's say meters per second squared. That means our acceleration is 0.67 times 9.81. That gives us 6.57 meters per second squared. That would be the acceleration at burnout. Okay, now let's look at non-burnout. So I'm going to drive responsibly. The acceleration will be static friction times g, which is going to be 0.75 times 9.81 meters per second squared. So in this case, 0.75 times 9.81 gives an acceleration of 7.36. So actually not that big of a difference, but this acceleration is higher, so that means you get more acceleration. So non-burnout is better, okay? This is a really tricky question. You wouldn't necessarily need to know how to do all this. This is just really cool how you use formulas and you manipulate them, and you can solve questions that you maybe didn't think you could. Okay? All right, last question. This one's a little bit tricky, but it's a really good question. So we are looking at a child who is on a toboggan. So they're resting on a horizontal place in the snow. We get a coefficient of static friction. We get a mass. We need to determine the horizontal force to get the sled moving. Okay, let's write down what we know. We know that the coefficient of static friction is 0.350. We know that the mass of the passenger combined with the sled is 40 kilograms. We are looking for the force that a person would need to use to get the sled moving. So we're really looking to find the applied force. Okay, let's draw ourselves a picture. So we've got Fg, which will be equal to Fn okay? We also have an applied force as well as some friction. Okay, the reason we know there's friction is because it gave us a coefficient of static friction. So that means there is some friction present. So let's say, I always like putting friction to the left wherever possible. So we're going to need to come up with what applied force is necessary to overcome that friction. So really we want to find when they're equal to each other. Okay, so this friction that's keeping the sled at rest, we need to know what it is. Because once we know what that friction is, that's how hard we have to push to get the sled going. So really we want to look at when these two are the same. Okay? So let's write that as a note. To get the sled moving, the applied force needs to be greater than friction. So let's find FF. That's how hard we will need to push. Okay, so we need to figure out what friction is, and we have to apply more force than friction. Okay, so in this scenario, net force is equal to all your forces added together. So we have gravity, we have the normal force, and then we have the friction force. We're trying to figure out what F applied is. It's not really there yet, okay? But gravity and normal force, they cancel each other out because they're the same. They're equal but in opposite directions. So really, in this situation, the net force is equal to whatever friction is, okay? Well, how are we going to find friction? Well, to find friction, we need to have the coefficient of static friction and the normal force. Well, we don't necessarily know what the normal force is, but we do know that normal force is equal to gravity, okay? So normal force is equal to gravity, and gravity is equal to mass times gravity, okay? So the force of static friction is going to be the coefficient of friction times mass times gravity, okay? So coefficient of friction is 0.350, mass is 40 kilograms, gravity is 9.81 newtons per kilogram, okay? So the force of static friction is therefore all those numbers multiplied together. So 0.350 times 40 times 9.81, we get 137.34. Okay, and that would be to the left. So this is how much friction is keeping the sled at rest. So this is how much friction keeps the sled at rest. So basically, we need to push with this much or more to get that sled to move. Okay? So, force of friction is 137 newtons. This is how much force is needed to overcome static friction. Okay? So you would need to apply a force greater than 137 newtons. Okay? That's how much you need to apply to get that sled to move. Okay, 137 newtons is holding it there. So to get it to move, you need to push with more than that. Okay? Okay, part B. Let the sled and the person on the sled be moving at 4 meters per second along a horizontal stretch of snow. The coefficient of friction is 0.0500. Determine how far the sled will move before it stops. Bad grammar. So let's write down what we know. Mass is still the same, 40 kilograms. We have a speed of 4.00 meters per second. Okay, it's going to come to a stop. So what that means is this is a V1, and we actually have a V2 of 0. Okay. Coefficient of kinetic friction, 0.0500. Notice how it's lower. 0.05 is a lot lower than 0.35. So once objects are in motion, there's less friction. Static friction is always more. We are also, well, what we're trying to find is how far the sled will slide before it stops. Okay. So if we're looking to figure out how far the sled is going to slide, we're going to go back to a good old kinematics formula. V1 plus V2 divided by 2 multiplied by time. Okay? Unfortunately, we don't have time. Okay, so let's pull out another formula from the archives that has time in it that we maybe have information for. We have V1 and V2, so we could use the acceleration formula to solve for our time. Except we don't actually have acceleration. Okay, so maybe there's a way we could find acceleration. Maybe if we used Fnet. Fnet equals mass times acceleration. We have mass, but we don't know the net force. Okay, so maybe we could figure out the net force based on our scenario. Okay, well, we know that the net force is equal to all your forces together. So gravity, normal force, friction force. Well, we also know that these are equal and opposite to each other. So really the net force is equal to friction. Well, with the information we have, we know the coefficient of friction, we know the mass, we could actually find friction because friction is equal to mu times normal force, which is really equal to mu times gravity force, which is really equal to mu times m times g. Okay? Normal force is really gravity. Gravity is really mg. So as long as we know mass, which we do, and coefficient of friction, which we do, and g is always the same, we could find the force of friction. Okay, so step 1, find friction. Friction is equal to mu, which is 0.05, times mass, which is 40 kilograms, times g, which is 9.81 newtons per kilogram. We punch all those things in, we get friction. One 19.62. We're going to keep as many decimals as we can because we got a long way to go to get back to the beginning. Okay, 19.62 newtons, which is really our net force. Okay, all right. Now we can go here. This will be step 2. Okay, F net is 19.62. equals. Now, let's keep in mind that this is friction, so it's going to be acting backwards or against our motion, okay? 19.62 equals 40 kilograms times A. Divide both sides by 40. Acceleration is going to be 19.62 divided by 40, negative 0.4905 meters per second squared, right? Because we're slowing down, so negative acceleration. Okay, now that we have acceleration, we can go up here. Now, if you want to rearrange your equation for t first, you can do that, or you can go ahead and solve. Basically, you end up with t is equal to v2 take away v1 divided by a, right? You multiply both sides by t, so we're left with t times a equals v1, v2 take away v1. Then we divide by a, so we end up with v2 take away v1 divided by a equals t, okay? So t equals v2, which is 0, take away 4, divide by acceleration, which is negative 0.4905. Well, this is good. We have a negative divided by a negative. That's going to give us a positive time, okay? So 4 divided by that 0.4905 gives us 8.1549 blah, blah, blah seconds. Let's keep a few decimals. Let's go 8.1549 seconds. Now that we have time, we can finally go back to the very beginning. Should number these. We can go back to the very, very beginning, and we have now enough information. So displacement equals 0 plus 4 divide by 2 multiplied by time, which is 8.154, etc., etc. So I'm going to keep that in my calculator. This is multiplied by 0 plus 4, which is really, oops, I'm going to go back. Okay, so 0 plus 4 is 4. 4 divided by 2 is 2. So 2 times this 8.15, blah, 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 we end up with 16.3. Now, this is a positive number, so we're moving to the right, because if we remember all the way back, so the sled was going to be moving in this direction, but friction is pulling back to the left. So when the sled is pushed and then comes to a stop, it's going to still be moving to the right. It's going to be slowing down. Because in this case, we would have had gravity acting, normal force acting, and then we just would have had friction, but the actual motion of the sled would have been to the right. Okay? So this question on the daily task, a question like this is broken down a little bit more. I ask you kind of for the steps instead of you having to go through and doing all these steps yourself. But this is a really good example of like the hardest kind of question that not everyone would be able to get, but it kind of separates those who kind of know what's going on from those who really know what's going on. Okay, good luck with the daily task.